I have made major changes to Linrad, and now I have version Linrad 06.00 preliminary, and it's revision 1069 on the repo. Now this version has many bugs still, but it allows me to do better measurements of sideband noise because it has distributed the work on more threads, so I can see a larger range. Here is from about 5 Hz up to about 10 kilohertz at the same time. This has been running for 25 hours, and now I can see the noise at 5 or 10 kilohertz is minus 180 dBc per hertz. Maybe one can see this better in the linear scale. As you can see here, it's close to minus 180. And when I expand the vertical scale, I can see it is a little bit below minus 180 and a half perhaps. The amplitude noise at wide separations is very similar. It should be exactly the same because the white noise floor is not related in any way to the phase of the carrier, and therefore the same in phase noise and as amplitude noise. I have been running the SDR IPs at the same time. The previous measurements I showed was with the sound card and the 2-channel hardware I have. But as you can see here, it is very different, the result I see with the SDR IP. The noise floor at 5 kilohertz here is minus 185. And that doesn't really make sense. And also the values I obtain at lower offsets here is not reasonable either. It is at, let's say, 50 Hertz. Here it comes at minus 157. While the result I see at 50 Hz with the sound card is here at minus 165. When I change from logarithmic to linear scale for the SDR IP, here is what I see, and now it is clear what the problem is. You see this periodical thing? Blue traces means that the correlation is negative. It means it is in antiphase. So, but a negative noise is not possible. This has to be an interference. And the reason that I saw below minus 180 is that this noise, that is digital noise from the SDR IPs somehow, there is a FPGA that does a lot of work, and it is running from 10 megahertz. Now the 10 megahertz signals are uncorrelated because one is phase locked to the other, but with a long time constant. But the FPGA, the effect of that, it's a program that goes in loops, and these loops are efficiently some kind of frequency dividers, giving rise to very low frequencies, such as in the range from 1 kilohertz to 10 kilohertz. And that noise is correlated because when you divide by something like 1000 from 10 megahertz to 10 kilohertz, then the signals become correlated because the time constant doesn't, well, I don't know how to explain it properly, but anyway, this low frequency noise is correlated. And the reason that it changes is that it is time shifted a little bit between the two units. So sometimes it comes in the phase of real phase noise, sometimes it comes in the opposite phase. And you can see the red dots, they are at the same level. They are what is in the 90-degree off phase. So that drops to low values when the signal is in phase, or out of phase. It should be lower here and higher here. Not very clear, but here you can see more clearly. So the conclusion is the SDR-IPs, I cannot use them to measure at large frequency separations. Well, I can look at the amplitude noise here also, and I cannot say that I really see anything. I can see some traces of the blue here. This is a graph from my previous video, nerds98. And the new points I have now are these triangles. They differ by about 1 decibel. But I now know that the floor is here at -180, so I have to redraw the curve slightly. So this is not a big difference. I am satisfied with the wide range noise from this experimental oscillator. But I'm not satisfied with the close range performance. It goes from 0.1 Hz here at 81 or maybe 82 dBc per Hertz. The green trace is the sum of the noise of the oscillator under test and the noise of my reference in channel 1. And the difference should be 3 decibels if the noise were the same. But it isn't 3 decibels, it's not even 2 decibels here. And if I look with a ruler and expect a straight line, you can see what the green trace, what I would want that to be. So I have a problem at 0.1 Hz offset with this oscillator. I have a theory about the reason for the poor stability at 0.1 Hz. That means in the time scale of 10 seconds or so. And that is that the supply voltage is varying in that time scale. So I'm going now to take a snapshot every minute for a while to see what happens. It is now 15.9053 volts. The supply voltage seems to be stable within about 0.5 millivolt. Now I turn on one single step on the power supply. That is 10 millivolts. And it takes a long time because I have a RC filter. And here is the new supply voltage. I will take a few shots of it with 1 minute's intervals. Here is Linrad in correlation mode 3, which gives Allan variation as well as frequency versus time. I changed the supply voltage back 0.01 volts, 10 millivolts, like that. And then I will look what is the frequency change. And it will take some time. but we can see it here. I can change the scale to see better. Maybe like this. And it seems the voltage step 10 millivolts gives about 2 millihertz. So 0.2 millihertz is the normal variations due to the power supply variations. And that's not too far from what you see from the red line here. And it hasn't stabilized yet, it will take some more time. The unusually large variations here is probably because I was moving some things around to place the camera back in front of the computer again. So when things are quiet, it's more like this, or what you see here. I have restored the original power supply setting and waited for quite some time to get the new voltage on the unit. It is a little different from before because the current consumption is different when it is not oscillating anymore. It has a low-level signal from the network analyzer only. The voltage on the unit is now 15.734 volts. And I have set the network analyzer to average over 4/8 sweeps, and then it gives me 0.94 degrees. And now I increase this power supply setting from 30.22 to 31.22. That's 1 volt. Now the supply voltage for the unit has stabilized at 16.694. And I restart averaging. So it now says average 1. And I wait for average 8. So here is what I found. About 0.96 volts gives 2.2 degrees. And before I found 0.2 millihertz per millivolt, and that means 2.2 hertz per volt. And now I found 2.3 degrees per volt. So that means about 0.1 hertz per degree. And this should be a consequence of the Q, which is 1,084,000. I am now measuring the voltage directly on the power supply, and it is rock stable. This is the power supply arrangement. It gives me a time constant of about 20 seconds. And the voltage variation I see here are not caused by voltage variations on the power supply. It is because the current through this resistor is varying. And that is flicker noise from the transistors in my unit. Here I have 12 FETs in parallel. I don't use that to the advantage that I could, because I have loaded it with a resistor on the drain side. So I can replace these with bipolars having lower capacitances and also lower flicker noise current, I think. So I will see if that reduces the phase versus voltage sensitivity of the unit. Before I start to modify this oscillator, I will use it as the reference oscillator while trying to improve what is now the reference oscillator, the channel 2, which isn't very good, as you have seen on the red traces on the sideband noise spectra. To do this, I connect the oscillator via the oscilloscope to the measurement system. And I note the level I have here because I want to restore it. Because what I'm doing is to set the frequency for the signal and the mirror image to come at the same place at 0. And that is by reducing the tuning capacitor and that will increase the power output. So then I will restore the same power output by reducing the coupling capacitor. So when I retune the capacitor here, the signal level is now much higher, and you can see the amplifier has gone nonlinear. So I will reduce the coupling capacitor now. So now I have restored the amplitude and changed parameters. So now I'm looking with the center at 10.0. And I can see I need to tune the oscillator upwards by about 3 Hz. Now the frequency is very close to 10 MHz. Doesn't mean absolutely 10 MHz, it means the 10 MHz I have from my reference oscillators. I can see that the amplitude is now down by about 15 decibels. That's because the sound card is AC coupled with very big capacitors in my case, so the frequency goes down to a fraction of 1 Hz. This was my channel 2 reference oscillator, which I will try to improve. I have supplied it with a nominal voltage 16.0, and the signal level is the same as with the other, but I can see it is a little bit saturated. Now I want to turn down the frequency so I can do some phase noise measurements. Here is Alan variation and frequency versus time. And we can see that the yellow trace, which is the difference between the two reference oscillators, is fairly flat most of the time, but not always. And we can see that the more high-frequency noise is strongly correlated between the channels, the red and the green trace. Here I entered the room. We can see that the channel 1 made a jump, while channel 2, the red trace, did not. I don't know what happened here, but something. Anyway, this looks promising. I will switch over to look at the phase noise instead. Already after 35 minutes, statistics is very good. And that is, of course, because the noise from my test object dominates. You can see it comes at the same place as the noise for the test object plus the noise in one or the other channel. I don't see any difference between the channels until fairly large separations, 10 to 20 Hz. But then it's not the noise from the oscillators, it's noise from the sound card, presumably. And if I look here, it's a very good straight line up to 0.2 Hz. Then it goes upwards sharply. I can read noise levels better in the linear scale. And still linear frequency scale, but I changed the vertical scale. You can see that the sideband noise here is very close to the noise of sideband noise plus oscillator noise. It's about 1 decibel only. But the imaginary part is down here. It's about 15 decibels below the real signal. So this is a good measurement. And here is the next section with linear scale. Above about 7 Hz, the signal is becoming too noisy. The first obvious thing I can try with this oscillator is to reduce the power. And the easiest way to do that is to just increase the tuning capacitor, means go down in frequency, while monitoring the signal level, which I have down here in the left lower corner. It's now about 1 decibel in the last position. I will tune it down by 3 decibels. So now I read 4 decibels here. So that is 3 dB lower. I will change the attenuator settings to restore full signal level into the sound card. The noise is a little bit lower, but not much. But when I look with the ruler, the bending doesn't start at 0.2 Hertz, and I don't know whether this is statistically relevant. But there is another problem, and there have been noise bursts. So there is some poor contact somewhere in the unit. Here I have touched the connectors in the feedback loop, and you can see this is a very strong interference. So I will clear all the spectra and see whether there is a difference now. Here is the result from the SDR IP units, and I find the wide range noise floor here at minus 163. That's enough noise to make the SDR IPs perfectly useful. You can see the imaginary part is well below. This is 6 minutes only on the sound card, and I can see the wide noise floor here also at the same level, minus 163. And what happens here? I have to wait for a little while. Here you can see when I touch the connectors. Now I have collected noise for 1 hour, so I will read out the noise values and compare to the previous result. The lower power level did not make much difference. There was a big difference at 0.1 Hertz, but for the rest of the frequencies the difference is small, except down here, but that's because of the longer measurement time. Now these results that I have, for example at 1 Hertz offset, minus 115, it doesn't compare well at all with old measurements. 1 Hertz, it's this point here, minus 122. That is 7 dB. And that was at the heated temperature of the thermostat. I did run it also without any thermostat at room temperature, and then it was about 3 decibels better. And these are old videos, Nerds 76 up to I think 79. Yes, Nerds 79. So something has happened to this unit. It has bipolar transistors. And this is the old schematic diagram I have. I may have changed something without checking what that did to performance. So I will study this a little bit more. But one thing is clear, also the old measurement indicated a noise floor in the region about minus 160 dBc per Hertz. I left measurement running overnight. It is 12 hours now, and I can see very good signal-to-noise ratio for the correlated phase noise. And this makes a very good straight line here, and it starts to bend a little at 0.2 Hertz and at 0.06 Hertz here. The deviation from the straight line is significant. And there is a second straight line here, the white noise, and exactly how the curve looks in this region I cannot say, because here is the zero frequency of the sound card. But there is one important thing, and that is there are glitches from the oscillator. It could be from my reference oscillators also, but I don't think so. I will remove this cable, which is doing the feedback from the limited output to the input, and place a cable soldered properly inside the box. I have done that with the previous oscillator also, and then when I want to do measurements I have to open the box and desolder that cable. Before I modify the unit, I will use it as an amplifier to see if I can find out where the noise comes from. So to do that, first I check my signal source, which will be the Wenzel oscillator. And I look at 1 Hertz. Here I see minus 120 dBc per Hertz. And when I was running that unit I'm working with as an oscillator, it was at minus 116. So it was much more noisy. So I should see that noise when I use this Wenzel as the signal source. As an amplifier with a Wenzel oscillator as the signal source, I see minus 120 at 1 Hertz and 136.5 at 5 Hertz. At 0.5 Hertz, the difference between the yellow trace and my 2 reference oscillators is almost 3 decibels, which means that the noise is the same from all 3. But at 2 Hertz, my channel 2 oscillator, the red trace, is only 1 decibel above the Wenzel. So this is the Wenzel plus my channel 2, and that is only 1 dB, which means that the channel 2 oscillator is significantly better than the Wenzel at 2 Hertz. That was at the power output with the dummy load at the feedback output. Now I do the opposite. So I put the dummy load, Well, I happen to short this point to ground. So now I have to replace the choke because there is no contact through it anymore. And here is the phase noise at the amplitude limited output. And it is minus 119 at 1 Hertz and 5 Hertz. 135.3 or something at 5 Hertz. When running the unit as an oscillator, it is significantly worse than the Wenzel oscillator by 5 dB. But when I run it as an amplifier, I see the same performance as I have from the Wenzel oscillator at 1 Hertz, but there is some degradation at 5 Hertz, all the way down to what I see it as when it runs as an oscillator. And I don't know quite what to draw for conclusion from this. Something introduces phase modulation when it is an oscillator, but not when it is an amplifier. The feedback cable is now internal in the unit without any connectors. And here is the phase noise at the amplitude limited output. And it is minus 119 at 1 Hertz and 5 Hertz. 135.3 or something at 5 Hertz. Well, the difference is very small. No difference at all at 1 Hertz, and at 5 Hertz it is now minus 137.5 perhaps. And it was 136 before. I think that is because there are no glitches anymore. And that those belonged to the connectors, I think, and now I see nothing of that. There is, however, one thing that I have forgotten about. There is a control input to the varicap that controls the frequency when I use this as phase-locked amplifier. I will short that input to ground because now it is open and presents a high impedance on the capacitance diodes, which should give some thermal noise on them. This didn't make any difference at all. probably because there is a big capacitor to ground inside the box. This is the arrangement I had for the frequency control. I have disconnected from the crystal here, and there is no difference at all in the sideband noise. I have disconnected the feedback cable now, and I'm injecting a signal from the network analyzer and set it to have the same output level at the maximum as I have when it is running as an oscillator. And this is what I see. The Q is 1,076,000. So there's nothing wrong with the crystal Q. I have reduced the power by 20 decibels and I checked the bandwidth once again. And now it says 1.14. So there is some compression. I have increased the power output by nearly 3 decibels. The output amplifier is probably heavily saturated now, but the noise is much better. At 1 Hz it is minus 123. Sorry, yes, minus 123 and a little more here. And that is 3 decibels better than the Wenzel oscillator, and the original value I had was minus 115, so it's an 8 dB improvement. And I can see that the oscillator is now significantly better than my channel 1 or channel 2 oscillators at very low frequencies. It's 4 decibels here. And at 5 Hz, minus 140. That's only 1 decibel better than the Wenzel, but it is 4 decibels better than I had originally on this unit. But there is a problem. I have had noise bursts here several times. So there is some component that is not really good. This is the waveform at the output, heavily saturated as you can see. There are 6 groups of these components at the output. I will change this resistor from 430 ohms, which gives 7 milliamps in each transistor, for 180 ohms and something like 15 milliamps. This is the waveform at the output. The power level is about 3 decibels higher now. The close range phase noise has not changed significantly. It is now 122.5 at 1 Hz. It was 123. And I think this is just the statistical uncertainty in the measurement. At 5 Hz it was 140 and it's 140 now also. The wide range phase noise with the SDR-IP units, I cannot see it anymore. It's below the limit where the internal noise of the SDR-IP makes the measurement useless. The sound card indicates that the wide range phase noise is about minus 170. This was the original design of the limiter that you could see in the old videos, up to nerds99. At some point I had changed it to put resonators in series at the input and output around the clipping diodes. And I thought that would be good, and it is. The problem is that I had other mistakes. I have made measurements at different power levels with the circuitry you just saw. The number here is the setting of the attenuator into the analyzing receiver in decibels. And I can see the noise at 1 Hz and 5 Hz. It was 116.5 at power level and 1 decibel higher, and then suddenly at significantly higher power I had a significant improvement, 1 116, and here it is 122. I had written 138 here, but I think that was a mistake. Anyway, I go back to 3 dB, but I have changed the tuning. So the audio frequency here is 39 Hertz, while it was 16 Hertz there. And that made a big difference. I don't understand why, but that is observed. And then at even higher power, it is even better. And then even more power, it is degraded a little bit. Then I made an effort to understand things, so I put the 50 ohm resistor to load the feedback output. There is a connector, so I can easily put a 50 ohm dummy load there. And then at the same power level as here, I note a strong degradation of performance. And then a 50 ohm dummy load on one connector and a 3 dB attenuator on the other to attenuate even further. Then the noise at 1 Hertz has increased a little bit, and that was at power level 4. And I was rather confused at these results because I couldn't make sense what it means. I thought it could be good to have a higher voltage at the output, so I could use a smaller feedback capacitor for the same signal level, because that should improve the Q of the filter slightly. So I put Schottky diodes, this is a Schottky diode, and looked at the results. And that was very discouraging. At 1 Hertz, the noise became about 105 decibels, and the signal level was a bit higher. I set the attenuator at 7 and at 5. But this is 106. I had 123 as the best observation. So, for some reason, these diodes are no good. They're microwave diodes. I then put 1N6263 diodes there. These are Schottky diodes, and I had good experiences with them in the past. Now I had only 2, so I could not try to put 2 groups in series. And indeed, this was encouraging. I observed 124 at 1 Hertz and 144 or 145 at 5 Hertz at power levels 2 and 4. And then I went up to power level 5 by changing the tuning capacitor, making it much smaller. And then I got a not quite as good result. But the frequency was very low, only 6 Hertz for the audio signal. So there seems to be some artifact caused by that. I'm not so sure. And then I tried to put a resistor to load it, and that dropped the amplitude, the power level, by 5 decibels, and the frequency changed by about 1 Hertz. But the sideband noise did not change. And then I tuned further. I don't remember exactly what I did, but the result was not much better. But the frequency was only 4 Hertz, 4.7. Here is what I have now. I always set the attenuator at the input of the 2-channel receiver, so I can read 1 decibel here. And now the setting is 6 decibels, so the power level is rather high compared to the previous measurements. And I have tuned the frequency, so the audio frequency is very low. It is 5.9 Hertz or something like that. And at 1 Hertz I see minus 124, which is very good. it is 4 decibels below the sum of this noise and the noise of my reference oscillators. And it is 4 decibels all the way. And then the curve bends slightly here. I think that may be an artifact, because here is the one of the sidebands is at the notch at the center, and the other sideband is contributing. So the true result is probably the straight line here, and that would be minus 146 or something. I am running the SDR-IPs in parallel, and for some odd reason I don't see the internal phase noise of the SDR-IPs. I see a nice measurement of the wideband noise floor at minus 172 dBc per hertz, which is much better by about 10 dB than what I had when I started this investigation of this, my channel 2 reference oscillator. When I move the vertical scale upwards with the UADC4, I cannot see the minus 172 dB noise floor, because there are overtones of 5 Hz still. But I can see that the noise is well below 168. And one thing, I don't see any noise bursts here, and I haven't seen that during all these measurements. So what I saw once was something that does not happen often. This is nerds99, and I found 122 dBc per hertz at 1 Hz back then, 2 years ago. Here is the output waveform into a 50 ohm load. The level of the 10 MHz component is 21.8 dBm. That is a little too much. To reduce the output power, I have reduced the number of turns on the collector winding. It was actually 25 before, and now it is 20. The power of the fundamental is 19.3 dBm now, and the overtones are significantly weaker. And here is the waveform, and this is a suitable level to my system, I think. Here is the phase noise at close range, a little better than 124. 124.6 or something like that. And when I try to estimate at 5 Hz, I don't know exactly how to fit here, but it comes in the neighborhood of minus 146. But measurement is inaccurate because of the zero frequency. And the noise floor, the wide range, has degraded just a little. It's now 171.5. And I suddenly understand why there is no interference here. That's because the frequency is so low. It means that the loops in the FPGA doesn't have loops that are so slow that they generate phase noise at very low frequencies. So before, when I was at 30 or 40 Hz from center, then there was modulation at 40 Hz that was correlated between the two receivers. But now, when the offset from the center is only was it 6 Hz, then I don't see any such problems. That's interesting. Try to remember this for the future. Now I will check the adjustment of the thermostat, and I do that by switching it off now first. And that causes the frequency to go upwards on this scale fairly rapidly. I will allow it for some time I will change the scale so I can see a little bit wider. And what I'm interested in is whether it will pass a maximum or whether it will continue upwards. Okay, it has passed a maximum. Like this. So the temperature was a little bit too high, and I want to come back to this, so I connect it again. And I wait for it to stabilize. Now I have put back the channel 2 reference oscillator, the one that I worked with and found finally very good performance with. And now I'm studying that amplifier that I started this video with, and which I will optimize, or try to optimize. It will be a faster process now because the channel 2 oscillator is much better. But as it turns out, at very close range, it is not so good. This is 0.6 Hertz or something like that. At 0.1 Hertz, channel 1 and channel 2 are very similar, at least when the device under test is as noisy as you can see the yellow trace here. At 1 Hertz I see minus 123 for this oscillator that I want to optimize, and the other ones are pretty close. And I have been running this for 11 hours, so the signal to noise ratio is very good. The audio frequency is about 28 Hertz, so I am fairly far from DC. When I look at the SDR IPs, it's still close enough so I can see the noise floor, which is at minus 176. That is because the power level is very low now. Here is phase noise again, and here is amplitude noise, much lower, and they are totally uncorrelated at very close range. There is some correlation at about 1 Hertz, but it's weak. A problem I can see is here. This does not look like white noise. Here is some structure, and here has been some events. So something is a bit unstable. Now I will tune the oscillator to the proper frequency. Oh, that was too far. Look at the S-meter graph here. It passed through 0. Yeah, now it drops. Somewhere around here will be correct. This looked very good some time ago, maybe half an hour. Well, now it disappeared. You might have seen when I started this part of the recording that the green trace was much stronger than the red. And you can see that here. Now there was a very strong something in channel 1. But channel 2 has not changed, so the yellow trace has not changed much. Only here when it went down, which is a bit odd, but it comes, obviously, that interference in antiphase somehow. Anyway, I don't know what happened, but I have been around here in the room, so I might have kicked something. Well, now again, some very strong interference. I don't know where to look for this. Now again, some very strong problem in channel 1, but channel 2 looks normal. I have had the SDR-IP units running in parallel, and there I see nothing. No glitches. In order to locate the problem, I have set AM mode, and I have applied a notch for the carrier here. And the notch is about 200 Hz wide. And then I look at the S-meter, and I have set it to show nearly 0 for what is outside the notch, but within the filter. And then, to demonstrate what this is about, I go and touch the attenuators. They are here, and I just go like this in channel 1, and then after a while in channel 2. And this is what I see. Channel 2 was not sensitive at all, nearly. And then I look at the SDR-IP, and here you can see what happened with channel 1. And this waterfall shows both channels. So that could not have been the problem, because I should have seen it here. But this demonstrates the measurement method I have here in the waterfall. So I will look at the usual suspects, all the BNC connectors, one by one. So I've touched many with very small response, and here is one that gives a very strong response. You can see here, as compared to those. It was this one, and I have now cleaned it, and I tried to touch it slightly like that. And now there is not any problem anymore. There are still problems with noise bursts. When I look here, this one and here, they are fairly narrow-banded. This could be wider, maybe it's just that it is stronger. And here is again something. It seems to me these have to come from the oscillator under test and not from the test system. When I look here, I find that the yellow trace is exactly on the green, which means that the noise in the oscillator is much stronger than the noise in the channel 1 oscillator. And the channel 2 oscillator is not quite as good as number 1, below 0.1 Hz. And when I look at amplitude noise, it doesn't look normal at all, not at very low frequencies. It is negative at 0.12 or so Hertz, despite the number of averages is 1100 after 11 hours. So that also supports the idea that this is caused by something in the oscillator and probably on the feedback side. So it comes only at very low frequencies, very close to the carrier, as we can see here. The wide range noise floor, flat above 5 kHz or so, is about -181. I can change the scale. And here I can see more clearly the flat noise floor is 181.2 or something like that. And it looks flat from here, which would be about 3 kilohertz. I suspect the problem could be caused by this trimmer capacitor, so I turn it back and forth several times before I set it to a new position. I have also increased the tuning capacitor to place the signal about 30 Hz below the reference oscillators. So here is the zero frequency and the second harmonic. And this looks now okay. Here the channel 2 oscillator is very noisy, so the imaginary part is close to the real part. But down here everything looks normal. An interesting thing is that there is a straight line here, and then it bends here and goes with a steeper slope. And the corner frequency for that is about 0.2 Hz. That is, as I have seen before. I will take down these numbers and save them, and then I will start to rebuild this oscillator. But that will be another video, the next one, Nerds 100, because now this video starts to become too long. It's easier to read the levels in the linear frequency scale. Note that there are no noise bursts anymore. This looks perfectly like white noise. This way I cannot go higher than about 10 Hz, where I read -152. And this is for a time of 3 hours and 20 minutes. The amplitude noise is not yet visible, but we can see here that the channel 2 oscillator, which I worked a lot with recently, as you have seen, it is very high in amplitude noise, below 0.2 Hz. Here it goes steeply upwards. At 0.06 Hz offset, the amplitude noise in channel 2 is at -80, while the oscillator is at -110. So there is a 30 dB problem at very low frequencies in the amplitude stability of my reference oscillator number 2. Now that doesn't affect the frequency modulation much. The wide range noise floor, the white noise, is well below what I can see in 3 hours with the SDR-IP units. This is what I have found. From about 5 Hz to 0.5 Hz, the points fall on the f-3 line, f to power -3. But below 0.7 Hz or 0.5 Hz, the slope increases to f to power -4.3. So this noise here and the noise here must be caused by different mechanisms. And that differs between all three oscillators. They have different behavior. So it's not caused by the crystal, it's caused by the electronics. And that is what I will look at in the next video.